This is really interesting because we've done a couple different pieces of work now in pharmaceutical space, and this was about um, neurological diseases. So these are essentially diseases that affect the brain that have many different types of challenges when you're trying to deliver drugs to the brain. Like you have to pass through the blood-brain barrier when you're so for your drug to reach there and for it to be absorbed correctly. We've done a couple different pieces of work. One we did on molecular similarity, so find molecules that can do that can get into the brain and be administered effectively. And then another one we've done on Creutzfeldt-Jakob disease or Alzheimer's disease, as well as mad cow disease, and what is it with those diseases that make them difficult to tackle and ultimately incurable? So what this is a method to analyze proteins that had misfolded in the brain. And so what happens if you get one of these diseases like Creutzfeldt-Jakob disease is that causes proteins to misfold in your brain. And we know all the correct ways that proteins are supposed to fold in the brain, but there's an inordinate amount of incorrect ways that they can fold. And so it makes it impossible to design a drug to go address this misfolding problem. You may think, it just is, it's impossible. And the way that they look at it right now, the way they find out how misfolds have occurred is they have to have those, they actually have to have a sample, and then they take a sample and they freeze it, and then they use something called cryo-electron microscopy. They freeze it, they put it under a microscope, they illuminate it in certain ways, and then it creates a shadow, and then they look at the shadow to figure out what the protein has folded into. And then this process takes weeks and weeks to analyze just one misfolded protein. And you're like, there's got to be a better way, right? And so the better way is to use computers to simulate how proteins should fold or could fold based on the constraints that we know about their properties. And then that can give us a library of ways that they've misfolded, and then potentially find ways to dock molecules to them to fix them or to mitigate some of the errors or the factors of disease. And so what we wanted to do was use a quantum computer to help us figure out these protein folds, these misfolds. And we looked at these prion diseases that I mentioned, Creutzfeldt-Jakob, mad cow, bovine spongiform, which are interesting because they still exist today. They can, if cows get mad cow disease or bovine spongiform, if you eat that cow, you can get Creutzfeldt-Jakob disease and start to, have misfolding proteins in your brain, and ultimately it's incurable. So what size protein what's the smallest size chain of amino acids that is folding into become this protein that would be useful for us to analyze? It turns out that's a chain of 200 amino acids is the smallest size, but they can go up to much, much larger sizes. Right now, that is intractable. We can't do that on a classical computer at all. And it, we'll never be able to, we'll never have enough computational power to figure out all of the different nuances of the way that a 200 amino acid chain could fold. And so, but with a future quantum computer, we could potentially simulate all of those different folding actions and model what these proteins would look like as they're misfolding. Right now, what we could do on our quantum computer was 8. So we have a long way to go. Well, this work is a little bit older, but we could do 8 proteins back in 2019 when we did this. And so as quantum computers are getting better, it'll be soon time to go revisit this problem and see if we can do some larger ones. But ultimately, using this approach, lattice-based protein folding is what we call it. It's a computational method. It allows us to figure out the misfolds and then potentially find molecules that can dock to them and help mitigate the diseases, is the theory. So hopefully it makes sense. Is what we're trying to do here is analyze these proteins, figure out ways that they could have misfolded. We know the 0.2% ways that they can fold correctly, but we need to know the 99.8% ways that they can misfold in order to help cure them. This is a common thing in pharmaceuticals. And so if they have researchers, they could be looking at this. A lot of people are looking at molecular structure. And so that's, as I mentioned, the precursor, where you're doing molecule analysis and you're trying to figure out the bond strength. And for material science in biology, you would be, I know there was work done by some of the startups and some of the other companies for the same problem for COVID, where you have a protein body that you want to, or a virus body that you want to have a molecule attached to in a certain way that prevents it from attaching to your human cells. So ultimately creating, a cure or a mitigation for the virus attacking the human cells. And so this type of modeling is done in different ways. If you have the structure, then you don't need to do this analysis. And so they quickly got the structure for what COVID was, and then they were able to focus on the small molecules that they would dock to it and what those structures would to fit in those protein cavities would be. But this is kind of not knowing the structure. How do you get the structure?